Hello students, in this video as well as in the next couple of videos we will be discussing about the feedback circuits, more specifically about the negative feedback circuits. Formally, formally this feedback circuit can be categorized either as negative feedback circuit or feedback circuit, or this negative feedback is also said to be a degenerative feedback circuit. Okay. So, this is one way of categorizing a feedback circuit. The other one is the positive feedback, and it is also called as a regenerative feedback circuit. So, this FB stands for the feedback, and basically this positive feedback circuit are generally used in waveform generation circuits like sine waves, square waves, and more specifically it is used for building oscillators inside the ICs. While the focus of this particular video is, as well as in the next couple of videos, will be based on this negative feedback circuit discussion. Okay. So, in the amplifier design, a negative feedback is applied to bring one or more of the following properties. Okay. So, let me write down those properties when you have a negative feedback. So, I will just use this NFB to denote this the negative feedback circuit. Okay. So, is used in an amplifier design to bring out one of the following properties. So, I will just list down the properties and then I will just discuss about each properties in turn. Okay. The first important property that one use in negative feedback in the design of an amplifier is to desensitize the gain. So, what it really means is that it makes the value of the gain to be less sensitive to variations in the values of circuit components uh, like mu or whatever it is. So, in general when we apply a negative feedback circuit in the design of an amplifier, it desensitizes those gain, and let me try to elaborate these things in more formal way later, but it makes the gain to be less sensitive. So, I will just write down that. It makes the value of gain to be less sensitive to variations in the values of circuit component. Okay. So, components, so I am just using all this short form notation, please try to follow it, and these variations may happen just because due to uh, changes in the ambient temperatures and stuffs. Okay. Yeah. So, the second important property that a negative feedback circuit can bring inside an amplifier design is the reduction in the nonlinear distortion. Okay. It tries to reduce the nonlinear distortion. So, what I really mean is that it makes the output to be proportional to the input. So, in other words, it makes the gain constant. And what I really mean by making the gain constant is that whatever the signal amplitude level that I feed into the input of an amplifier, the gain of the circuit remains constant. Okay. So, it is independent of the input signal level. And the third important property that it could bring when we employ this negative feedback circuit in an amplifier design is this reduction in the noise. So, it basically minimizes the unwanted electrical or signals that are being generated at the output. Okay. So, at the output of the amplifier. Okay. So now these unwanted electrical signals can be either generated using the circuit components by themselves. So probably we will be discussing about these things when we discuss about the noise analysis of a circuit, or it can also be generated outside the circuit due to some clock that runs in parallel to any sensitive wires and stuffs. Okay. So basically due to interference effects. Okay. So but when we employ a negative feedback circuit, those unwanted electrical signals that are being generated at the output can be minimized. Okay. And the fourth important property that it brings to the circuit is the control of the input as well as the output resistances. Okay. So what it really means is that we can either rise or basically increase or decrease the resistances, and these resistances can be again classified either as input resistance or output resistance, and one could either rise those resistances by selecting appropriate feedback topologies. Okay. So based on these topologies that has been employed, the normal amplifier input resistance and the output resistance can be either increased or decreased. Okay. So that is what it means over here. And finally the fifth important property, probably you might have been much more familiar with it, is the extension of the bandwidth of the amplifier. Okay. So in general it extends the bandwidth of the amplifier when it employs this negative feedback. Okay. So this particular discussion about the extension of the bandwidth will be more discussed when we discuss about the stability analysis. Okay. Yeah. So now in a way when one tries to employ this negative feedback amplifier in an amplifier design, it brings out uh, all these properties in general. Okay. So now all of these properties are in general are brought into the amplifier design at an expense of reduction in the gain. Okay. So which is more important. So all of these properties that I have mentioned, probably I will just use a different color. So these are the desired properties, and in order to bring these desired properties into the circuit, uh, one has to give up something, right. So that is, these are being obtained at the expense of reduced gain. Okay. So the gain of the circuit becomes reduced when we try to employ a negative feedback circuit in an amplifier design. Okay. So that is what it really means, and as you may have already studied, that this reduction in the gain could be modeled as AF. AF stands for the amplifier with feedback circuit, the gain of the amplifier with the feedback, and that is equal to the open loop gain where there is no feedback around this medium or the gain, divided by 1 plus A beta. Okay. So now that I just want to bring out few of the terminologies that I have denoted here. So as I said before, the AF basically denotes the closed loop gain of the amplifier. Okay. Whereas the capital A without suffix F denotes the open loop gain of the amplifier, and the beta denotes basically the feedback network transfer function. Okay. So I will just use this TF to denote the transfer function of the feedback network. Okay. So and one could also define this denominator of 1 plus A beta as something like gain reduction factor Uh, so this quantity of 1 plus a beta basically is defined as gain reduction factor, which means that it defines the factor by which the circuit gain is desensitized. So what it really means is that as you could able to see that the capital A could be something like a product of GM times R out, right. So any circuit will have this particular form of expression in it, in case if this A is trying to represent a voltage amplifier. Okay, so in that case, just because of this denominator of gain reduction factor, the gain of the circuit in general is getting desensitized. Okay, so let me elaborate all these points in the later part of this particular session, but in general, it defines the factor by which the gain reduction factor defines the factor by which the circuit gain is desensitized, as well as the input resistance of a voltage amplifier is raised, and it also defines a factor by which the bandwidth of the circuit of the feedback amplifier circuit is being extended. So in general, all of these properties that we are gaining out of this negative feedback could be defined with respect to this gain reduction factor. So sometimes we call this gain reduction factor also as the amount of feedback. Okay, yeah. So in short, what it really means for us is that the basic idea of a negative feedback circuit is to trade off a gain for other desirable properties. Okay, so we are giving up the gain in favor of all those 5 different properties that I said earlier. Okay, now under certain conditions, these negative feedback in an amplifier can become a positive feedback. So even though this particular feedback that I have written down here represents a negative feedback gain expression, sometimes these negative feedback expression can become a positive feedback, and they may tend to cause oscillation at the output, and the circuit might become some sort of unstable circuit. Okay, but we will discuss about these conditions in the later part of the video, like later part of the syllabus, as I said, when we discuss about the stability and compensation technique. Okay, but here we are interested only in the design of stable amplifier designs. Okay, so and again I try to bring out one of the important point is that it is not implied that when this negative feedback circuit becomes a positive feedback circuit, it does not implies that this particular positive feedback circuit always lead to instability. In fact, this positive feedback circuit is useful in a number of non-regenerative applications like filter designs. Okay, so anyhow, these are not part of our syllabus as of now. So I just want to bring out that not all positive feedback circuit leads to an unstable or unstable amplifier design. Okay, so that is what I just want to bring out. Sometimes one could use this for positive feedback in a proper controlled environment, and then can utilize for the design of non-regenerative circuit designs like filters. Okay, so now let me draw a signal flow diagram of a general negative feedback structure. Okay. Such that I can just prove this particular expression based on this signal flow diagram of a more general negative feedback structure. So in short, there will be a source through which the signal, which I take it as x suffix s, okay, that has been generated, and later on there is some sort of mixing circuit is there, and after this mixing circuit we end up having a signal which is xi, and this xi is fed as an input signal to the basic amplifier, which is A. So as I said earlier, this A denotes the open loop gain of an amplifier. So this could be just a simple CS amplifier, or this could be just an op amp. Okay, yeah. So it is pretty clear that the signal input that we are feeding to this open loop amplifier A has the suffix of I. Okay, whereas when we discuss from the overall perspective of a negative feedback, the input signal has a suffix of S here. Okay, so let me try to explain each of these signal notations that we are about to follow in the later part of this particular video, but as of now I'll just try to emphasize few of the points which comes in on the way. Okay, now after this amplification through this open loop gain, the signal that we would end up having is generated with X sub naught. Okay, and that has been fed to a load. And in order to create a negative feedback, what we generally wanted is a kind of sampling this particular signal X naught and feedback to a feedback network. Okay, and we feed a sample of this particular circuit, sorry, this particular output back to a feedback network. Okay, so in general, this beta denotes this feedback network quantity here, and the output of this feedback network generates an output which is denoted as X suffix F. Okay, so this is the feedback signal. I hope that it is clear. So basically this feedback network samples the output signal X naught and mixes the output of this feedback signal, which is XF, along with this source signal such that it generates this Xi. So in short, the Xi is the input signal to the open loop amplifier which has a gain of A, and XF is nothing but the output signal of the feedback network, and this XF in general is mixed with the source signal, which is in this case XS. Okay, so please ensure that you follow these notations, like what we really mean by the suffix of S and suffix of F and suffix of I. Okay, so each individual terms will be utilized later while we design these amplifiers. Now, and this signal Xi could be returned as XS minus XF. Okay, so in order to make this negative sign, I have to ensure that the summation is added and subtracted with these signals. Hope that it is clear. Okay, and also there are a few notations that have been added to this particular signal flow diagram of a negative feedback circuit. Those are the signal A with a arrow mark at the top, and the feedback network, it's not the signal, sorry, is the transfer function of A with an arrow at the top, and the feedback network beta with an arrow at the top. So these arrows in general denotes the open loop gain as well as the feedback network or unidirectional circuits. Okay, so the arrows in turn defines that they are unidirectional. So what I really mean by those unidirectional circuits is that there is no reverse transformation from output towards the input. Okay, so say for example there is no signal flow from the signal X naught towards Xi, so that is completely nil, and even here there is no signal transfer from XF towards the X naught. Okay, so due to which these arrows in general denotes that these circuits are unidirectional circuits. Hope that it is clear. And also the signals which have been denoted with X can be either a voltage or a current signal, okay, and we will be replacing those x with either V or I in order to denote them whether we are dealing with a voltage signal or a current signal. And one could see that this subtraction of x suffix s minus xf in general denotes that we are dealing with a negative feedback circuit, okay. Now basically I can also bring out few other terms based on this circuit. This is one of the expression, and one can also define few other expressions like this xf, which is basically beta times that of the x naught, because it samples the signal x naught and feeds through this beta network in order to generate the xf, and the x naught, the output signal of the amplifier, is nothing but the product of gain of the medium into the input to the medium, okay. So using all these three equations like 1, 2 and 3, one could basically define the gain of the closed loop amplifier as I stated earlier, that is a sub f as x naught output divided by the input, okay. So as far as the feedback network is concerned, the input signal is basically this particular signal, which is x sub s, okay, whereas the input to the open loop amplifier is xi. So please ensure that you make those differentiations between those signals, okay. So I could define the transfer function of the feedback network as the output signal x naught divided by the input signal, which is xs, okay, whereas the open loop gain has a transfer function which is x naught, the same as that of my output signal of my uh, closed loop transfer function, but the input is not xs anymore, but it is xi, clear. So this is the transfer function of the open loop gain, and this is the transfer function of the closed loop gain, and one could write this transfer function of this closed loop gain in terms of transfer function of the open loop gain expression as a divided by 1 plus a beta, okay. So in order to get down to this equation, one has to utilize all those three expressions that has been listed towards the left, and when we try to plug in those equations, we would end up having this, okay. So this is a very straightforward algebra in order to prove this particular statement, and I will skip this particular part of proving those this particular formula, okay. And now apart from being defining this 1 plus a beta as the gain reduction factor, one could also talk about this particular factor, which is a beta. There is a specific name for this a beta, and we call this quantity of a beta as loop gain, okay. And let me use a different color in order to denote the one plus a beta as the gain reduction factor, okay. So this is different, whereas loop gain is just the product of the a times that of beta, okay. Yeah. So now there are a few things that we need to concern when we discuss about this a beta term, okay. Now with respect to a beta, that is the loop gain, there are few things that we need to keep in our mind in order to ensure that we are following the right way of doing the analysis, okay. The very first thing is specifically for the feedback network, okay, to be a negative feedback, okay, one has to ensure that this loop gain has to be always a positive quantity, okay. So for any feedback to be a negative feedback circuit, then this a beta term must always be a positive quantity, okay. Now This means that the feedback signal, which is xf, should have the same sign as that of the source signal xs. Okay, so both these signals should have same sign. Okay. So what it really means is like say for example I have a source signal which is a positive cycle, then even this feedback signal xf should also have the same positive cycle. Okay, you cannot have an opposite phase. Okay, both has to have the same phase in order to have this a beta to be a positive quantity, and if at all if this a beta loop gain term is positive, then the type of feedback that we have employed can be defined as a negative feedback. Okay, and that is the real meaning of a beta being a positive quantity. Okay, now having both these signals xf and xi, x sub s, okay, having the same sign, what it really means is that this signal, the input signal to the open loop amplifier, which is nothing but xs minus xf, okay, in general becomes smaller, provided if both these signals are having the same phase and same sign. Okay, now this is one of the reason why when I was stating about an important property, which is reduction in the nonlinear distortion. Okay, so I said that irrespective of whatever the signal that level that I provide, which means that irrespective of whatever the signal level that I provide to this x sub s, okay, due to this feedback that comes and reduces this input signal level, the actual level that goes to the amplifier is just the reduced signal level. Okay, so due to which the amplifier in general have this reduced nonlinear distortion, just because the input that we actually feed is not the xs, but it is this xi quantity, and which is always a small. Okay, so I think I can talk about it when we discuss about the same quantity. Let me talk about it in much more depth. Okay, so let me move on to the second point with respect to the loop gain. The second important point is that for a positive value of this loop gain, the let me write it. Okay, for positive value of this a beta, the feedback gain, which is AF, will be smaller. Okay, this will be always gets reduced by this factor of gain reduction factor. And the third important point is that in case if this a beta or the loop gain is much larger than the value of 1, then one could step down this a beta. So previously this feedback gain is defined as a divided by 1 plus a beta, and in that if this loop gain becomes much larger than the value of 1, then one could approximate uh, this quantity as a divided by a by beta, and one could cancel out the common terms here, and that would end up having a value which is equal to 1 by beta. So clearly this feedback gain expression has a very little dependency on the basic amplifier. Okay, so it entirely depends on this feedback network and doesn't depend on this open loop gain. So why this property is so desirable is that in general the open loop gain uh, of the basic amplifier, so uh, rather than telling it as open loop gain, I will just tell it as basic amplifier. um, a The gain of this basic amplifier is usually uh, it is a product of GM times R out, and when we look carefully, this value of GM that we have in general is proportional to the small signal parameter GM of the transistor, and we know that this particular parameter in short is again proportional to this mu n COX, so which are basically the manufacturing parameters, and these mu n COX parameters in general have a wide tolerance value. Okay, so what it means by this wide tolerance value is that they tend to vary a lot, and due to this variation, the gain of the open loop, or basically the gain of the basic amplifier or the open loop gain in general varies with either with respect to the temperature or with respect to the process variations. Okay, so there are a lot of variation that happens across this particular parameter A, and one cannot use this gain as a constant value. Okay, and so in short, if we could be able to build an amplifier with a feedback circuit, and that amplifier has a gain which is just defined by the feedback network as 1 upon beta, then this particular quantity does not have any sort of dependency on this open loop gain, or it does not have any dependency on this process parameter variations in short. Okay, so this is much more important property, having this a beta term to be much larger than the value of 1. Okay, and the fourth property that we one need to have is the same thing. Okay, so which is again having this a beta being much larger than the value of 1 signifies that the feedback signal, okay, um, as I said, the feedback signal can also be defined not just in terms of x naught, as we know that this feedback signal can be defined in terms of x naught as beta times that of x naught, but one can also define this feedback signal xf, which is this particular signal, in terms of x sub x, sorry, x sub s, or the source signal. I will just call it as source signal. One can also define that particular signal, feedback signal, in terms of source signal as a beta divided by 1 plus a beta, and in case if this a beta term is much larger than the value of 1, then one could approximate this value of xf to be exactly equal to xs. Now this implies that the input signal that we are feeding to the basic amplifier, if the magnitude of this particular signal is same as that of the magnitude of this source signal, then the xi, which is defined as the difference of source signal and the feedback signal, almost becomes equal to 0. So this particular input signal of the basic amplifier basically approaches a value that is closer to a value of 0. Okay, so this means with respect to the amplifier, the input signal, like in case if we consider this xi as some sort of error signal, which you would have learned in your basic electronics, that one could visualize the input signal of an amplifier or an operational amplifier or op amp as an error signal, then having this a beta term which is much larger than the value of 1 would reduce this error signal value closer to a value of 0, and that is what we mean. Okay, now I can also define the same xi, rather than defining in terms of the subtraction of source minus the feedback signal. I can just plug in this quantity of this term onto this, such that one would end up having an expression of xi, that is the input signal to the basic amplifier. It is not the input signal of the feedback amplifier. Please ensure that we are going in a right track. Okay, the Xi is a signal that goes to the open loop amplifier or the basic amplifier A, okay, and that could be defined in terms of Xs, where this is the source signal that is fed as an input signal to the feedback amplifier, okay. This is the input signal of the feedback amplifier, whereas Xi is nothing but the input signal of the basic amplifier or the open loop amplifier, okay. Having just A, okay, whereas the feedback amplifier will have this transfer function of A sub f, clear. So hope that you are clear with it. So now that when we plug in those quantities onto this expression, it becomes pretty simple, that it becomes like 1 by 1 plus A beta, okay, and when this A beta term is much larger than the value of 1, then as this A beta approaches 0, the Xi in short becomes smaller and it would approach to a value which is closer to a value of 0, okay. So it is this reduction of the input signal Xi to the basic amplifier uh, results in increase in the linearity of the feedback amplifier, okay. So let me demonstrate this. So why one needs this Xi to be much smaller in order to increase the linearity of the amplifier, okay. So in short, I will just write it, that in turn it increases the linearity of the amplifier, okay, having this Xi to be very small. So let me try to demonstrate this statement with a plot of ID versus VGS, and one could draw the graph, as we know that till the value of VGS reaches the value of VDH, there will not be any current through this circuit of a transistor, and after this the current starts flowing, right. And with the help of this graph, let us try to evaluate the small gm parameter, okay, at a fixed bias voltage VGS. So we want to fix a bias voltage. Let me fix that particular bias voltage somewhere here, where my transistor is basically on, and we just want to evaluate this gm, and we know that this gm is nothing but dou ID with respect to dou VGS, and this VGS is basically kept at VGSQ, okay. Yeah, so now as you could see that if this variation of our input signal, where in this case the input signal is the small signal VGS that I am trying to apply, okay. So as you increase the magnitude of this input signal, what happens is that when you look closer to this particular regime where I have the swing, you could see that this particular swing creates an arc across this particular cara, and this arc, when we zoom in, it basically so let me draw the zoomed version of this. I have a curvature, okay. So this is the curvature that I have between the extremes of the input signal high and low, okay. So whenever I have this, so having this kind of cara of curvature basically leads to a GM which is not a constant value, okay. This particular GM will tend to have a nonlinear cara or nonlinear quantity inside this. So now one could make this GM constant if we could be able to reduce the swing, the amount of swing that I try to apply onto this VGSQ. So say for example, if I could somehow reduce this GM, so let me first mark my Q point. So rather than having this wider swing across this Q point, if I could able to reduce this swing around a very tiny quantity, then when we just look for this amount of swing across this particular uh, yellow color signal, which is a quite smaller signal, clearly you could be able to see that this graph tends to be much more straight line. So, which means that this quantity of GM will then become a constant for this particular type of signal, whereas when you have a signal which is of greater magnitude, then it also includes some sort of curvature. It is no more a straight line, it includes a curvature. This curvature in turn makes this GM not to be a constant quantity, okay, and that is what we really mean. So, whenever we have this GM which is not a constant, then it introduces nonlinear distortion into our gain expression, clear. So, that is the reason why when we have this loop gain factor which is much larger, then the input signal will approach to a value which is closer to a value of 0, which means that in this case the swing, okay, the amount of swing, if I could be able to reduce much smaller, then that small signal variation maps onto a very small segment of this curvature, and that small segment in general will be a straight line, and due to which we will get a constant GM out of this circuit. And this is something that you have to imagine, okay, through whatever I said. So you can just pause the video and then revisit the same thing that I said right now, okay, in case if you have not followed it. So these are some of the most important properties that we get when we have this A beta or the loop gain, which is much larger than a value of 1, and if this A beta is a positive quantity, clear. So these are the introductory part, and let me just move on to something about this feedback circuit. Let me just give a quick review of this feedback amplifiers, but probably I will begin with this with the discussion of feedback amplifiers, uh, taking each individual type of amplifiers, working out the gain expression for the feedback amplifier, and as well as uh, the increase or reduction in the input and output impedance of those feedback amplifiers. All those things we will be discussing later on, probably from the next session onwards, clear. But as of now, today I just have covered the basic introductory part of the negative feedback amplifier circuits, okay. So let me discuss about 4 basic feedback topologies, okay. So basically, in order to, before we start discussing about those feedback topologies, one could categorize the basic amplifier. So whenever I say a basic amplifier, I really mean the open loop amplifier design, okay. Okay. So one could basically categorize this basic amplifier gain A into 4 categories. Somehow my pen is not functioning properly. Yeah. So the first type of amplifier that we will be discussing in the coming session would be a voltage amplifier, which I guess everyone would be much more familiar with it. The next one, the next type of amplifier that we will be discussing is the current amplifier. And the third type of amplifier that we will be discussing would be the transconductance amplifier, and the fourth one is the transresistance amplifier, okay. So these are the 4 categories of amplifiers that one can have, and these amplifiers has to be added with appropriate type of feedback topologies, such that the A becomes AF, that is the feedback amplifier gain stage. So there is no changes between them. So the voltage amplifier of the basic amplifier will become as a voltage amplifier with a feedback, okay. So whereas the current amplifier could then be turned into a current amplifier again, but with the feedback. Okay. So again in the same way the transconductance as well as the transresistance, so they all have to be added, but in between them what makes difference between this basic amplifier and this feedback amplifier is that the addition of this feedback network. Now in the first case the type of feedback network that we would employ will have a transfer function which would sample an output voltage and then mixes a voltage here. Okay, so it will have a transfer function which has a ratio of V by V, whereas the second one will have a transfer function which will have a ratio of current by current, and the third and the fourth will have a different factors here. Okay, so when we have a transconductance as our amplifier, let us try to see visualize what are their inputs and output signals, and then later I will talk about the input and output signal of the feedback network. Okay, um, so let me write them as input and output signals of these amplifiers, either as a feedback or either as a basic amplifier. So in the case of a transconductance amplifier, the input signal is basically a voltage signal, whereas the output is a current. Okay, whereas in the case of a transresistance amplifier, the input signal is basically a current, whereas the output signal is basically a voltage signal. Okay, and for these kind of structures we want this beta network to be an opposite nature. Okay, so which means that uh, we need a V by I, which is nothing but uh, the transfer function of the feedback network, whereas that has to be adopted for this transconductance amplifier design, and the feedback network should have an I by V transfer function when we employ that feedback to a transresistance amplifier. Okay, so let me fill the other quantities that I have here. So basically the input of a voltage amplifier is basically the voltage signal, the output signal is again is a voltage signal, whereas the input of a current amplifier is again a signal which is made of current, and the output is also again a current. Okay, so these are some of the quantities, so probably you might all be familiar. So in the next class or in the next couple of lectures we will be discussing about each individual structures with a particular flow. Um, since the time is running up, I just want to okay, so let me stop it here. Probably I will just come to Zoom, and if you have any doubts we can just discuss in the Zoom session. Thank you.